Okay, welcome to Unit 3.2, Day 2, Differentiability. Yesterday we covered the finding where a function is not differentiable, and so today we're going to use calculators to approximate derivatives numerically and graphically. So most of the functions we encounter in calculus are differentiable wherever they are defined, which means they will not have corners, cusps, vertical tangent lines, or points of discontinuity within domains. Their graphs will be unbroken and smooth with a well-defined slope at each point. You're going, okay, so why are we doing this? Because there's always those exceptions. So a good way to think of a differential function is that they are locally linear. That is, a function that is differentiable at A closely resembles its own tangent line very close to A. In the jargon of graphing calculators, differential curves will straighten out when we zoom in on them at a point of differentiability. So that's what we're going to do. You don't need a calculator for this one because this is what we did on this one. I gave you three different views of a differentiable function, f of x equals x cosine of 3x. We have zoomed in here at the point to 1.9. So what we can do is go 2, 1, 2, is that part? 1, 2, and then 1.9, which is going to be right around here somewhere. Okay, and then they did again. So notice that where they're telling you that the window is 1.7 to 2.3. So 1.9 is probably about here, maybe a little over. And then we come up, it's probably somewhere in here. But you can see that this one, you can definitely see the curve going on. This one, you can still see a little bit of a curve. But then when we zoom in one more time, that looks like an entirely straight line. I mean, I can go in here and get my lines and draw a line, and you can see that that is almost a perfectly straight line. Let me get rid of the pen. You can see that this is almost a perfectly straight line, where over here you can see that there's still quite a bit of a curve going on, and obviously, well, there I need to turn it a little bit. But well, that one looks quite straight, but it's small. But this is the one that I really want to look at, the fact that I try to make that guy parallel and I end up getting a really good secant line. But I come over here and our lines are almost perfect. And that's the point that they were trying to make on this one, is that you can zoom in on a point and have it basically straighten out for you. So let's talk about doing derivatives on a calculator. Derivatives on a calculator. Many graphing utilities can approximate derivatives numerically with good accuracy at most points of their domain. For small values of h, the difference quotient is often a good numerical approximation of f prime, which is what we used in the last section. However, the same value of h will usually yield a better approximation if we use a symmetric difference quotient, which is what your graphing calculator uses to calculate NDR. Don't worry about that. If you have a TI-83, I'll have to work with you on the NDER. But know that if they say NDER, they want a numeric derivative of f at a point. Anyways, the calculator, this is a calculator jargon. But your calculator does this, f of a plus h minus f of a minus h all over 2h. The numerical derivative of f as a function is denoted by this. The numerical derivatives we compute in the book will use h equal 0.001. Hopefully you guys are going, hey, we've done that 0.001 before. Yeah, we did. So using a calculator, don't worry about this definition here, because that's the calculator. We have no control over what the calculator uses. This says find the numerical derivative of a function. So the best I can do is tell you how to calculate this into the calculator. So if you're on your main screen, you're going to do an alpha and then window. And the derivative is the third one down. So just type in 3. So then what you get is you get a D in a box, and then parentheses, a box, and then you get a box equaling a box. And you're going to, so the question is, what am I putting in? Well, you're going to put, I'm going to do my best to type this in, so I'm going to put it in red, so it looks a little different. This is going to be x. And if you notice that this box went to x when you put this one in. You're going to put your function in here, so x squared plus 3, and it'll nicely expand for you. And like I said, when you put this x in, this x jumped in, and then it says, at what value of x do you want this derivative value? Well, when x equals 2. So you'll put 2 in here. Put in 2 there, and you get a value of 4. So f prime at 2 in this one is equal to 4. And that's what you get. So it's always going to be alpha window 3, and then this is what you're going to get, and you're just going to plug things in. So let's try another one. This time I want x cubed at 2. So it's going to be d dx, and then type in the function x cubed, where x equals 3. You're going to type that into the calculator, and you're going to get f prime at 2 is equal to 12. And you can quickly double check that. Hopefully you have a calculator while you're looking through this. If not, you're going to practice it. You'll practice it when you come back to the classroom. Okay, so they give you another example. Find the numerical derivative of the function when x equals 0 on this one. So again, you're going to do the alpha window 3. You get d dx. You're going to type in x. Type in the 4x minus x squared, where x equals, and in this time you're going to put in 0. And then you can identify f prime at 0 for this particular function is going to equal 4. Now the calculator may give us numbers with a few decimal places behind it. Sometimes it does, sometimes it doesn't. So you can just kind of play with it. Okay, because of this method used internally by the calculator, you will sometimes get a derivative value at a non-differentiable point. This is a case of where you must be smarter than the calculator. Remember, the calculator is no smarter than what you put into it, but in this case, you need to be able to recognize going, well, I'm going to put it in, but the value I get out is not going to be a good value. So let's look at this one. Use a calculator to compute the numerical derivative of f of x equals absolute value of x at x equals 0. Is this function differentiable at the indicated point? Well, if we put this into the calculator, so let's put it first into the calculator. Yes, I'm playing with the calculator. Absolute value of x. I don't have this written on my paper that I did it, so I don't know what the value is. Oh, I get 0. So when I did this one, when I did on this particular one, f prime of 0 equals 0. But this is an incorrect value. Because it says, is the function differentiable? No. Why? Because f of 0 equals 0. It's not that big a deal, but it's a corner. It's a corner. And so even though our calculator gave us a value, if I gave this problem to you and you said that, oh, f prime at 0 is 0, I would have to mark it wrong. I know the calculator gave you a value. However, the problem with it is the fact that if this is a corner, and if you look at the derivative, If your x values are positive, it's going to go this way, and if your x values are negative, it's going to go this way. And this is going to be at m equals 1, and this is going to be m equals negative 1. But if you do limits, you're going to get 1 and negative 1. It doesn't work. Okay, so what about the next one? If you type this into the calculator. So this time we'll type this one into the calculator. X raised to the 2 divided by 3 power, delete, delete. And I want also this one evaluated at 0. And again, it gave me f prime at 0 equals 0. But why is this not? And this is where you need to recognize this. Even over odd is a cusp. That special case of a corner. Okay, let's try another one. Your calculator to compute the numerical values on this one is a function differentiable. By the way, this one is going to give us f prime at 3 to equal negative 2. Let's see, 4 minus 6, yeah, negative 2. Is the function differentiable? Yes, it is. It's a polynomial. It's a polynomial, and all polynomials are differentiable from negative infinity to infinity. So it doesn't matter what the polynomial is. They're differentiable from infinity to negative infinity, or vice versa. They're always differentiable. Okay, so next I want to be doing the graphing. It says let f of x equal natural log of x. Use NDR to graph y equals f of x. Can you guess what f prime of x is by analyzing its graph? Now I think I have these down here, so we can talk about them here in a minute. But let me tell you how to go into this on the calculator. Go to y equals. So you go into y equals, and then you're going to do the alpha window. And you know the drill is going to give you that D with a box, with the parentheses, and then box equaling box. So now I go back to a different color. And what you're going to plug in now is still x here, and then that will change this guy to x. You're going to type in natural log of x. But instead of putting a number here, you're just going to say when x equals x. That tells the calculator to just say whatever x is, solve it and graph it, and it will graph your derivative. Well, in this case, this is your derivative. This is the table for your derivative. Now again, I need to remind you, this is f prime of x. So the question was, can you look at this and tell me what the graph is? Can you look at this and tell me what the graph is? So if you put in 0.1, you're getting back 10. Put in 0.2, you're getting 5. So the question is, how am I getting basically the reciprocal? This is 1/10, and I'm getting back 10. This is 2/10, and I'm getting back 5. And so on and so forth. So 0.1 equals 1/10, but I'm getting back 10. We're getting a reciprocal kind of thing. So actually, 0.1, this is what I'm putting in. This is what's going in. But really what I'm getting is a reciprocal, which is going to be 1/x. So you've just learned the derivative of natural log of x is 1/x. It works every time. Okay, so let's look at this one. Oh, this time they gave you cosine. So now you guys know what you're doing. You're going into y equals, alpha window, yada, yada, yada. And on this one, when you graph it, you're getting this curve. Now this is 0 and this is 2 pi. I'm going to let you guys know that right now. This is 0, this is 2 pi. At 0, it's 0. At 1.5708, guess what? That's pi over 2. You get 1. 3.1416, guess what? That's pi. You get 0. I'm going to let you know that 4.7 blah, blah, blah is 3 pi over 2. And then this is 2 pi. Now, if you know your trig, you're going to go, oh, hey, this is the sine wave. So, if f of x equals negative cosine of x, then your f prime of x, dun, 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 is sine of x. This is when it comes really nice to know what your graphs are going to look like and what you're going to expect out of them. Okay, normally you would not be, at this point in the game, expected to be able to look at a graph and know that it's the derivative of another one. But you'll get there. Okay, so this is the one. Differentiability implies continuity. If f has a derivative at x equals a, then f is continuous at x equals a. The converse of this theorem is false. A continuous function might have a corner, cusp, or vertical tangent line, and hence not differentiable at a given point. But, so if you have the derivative implies continuity, but continuity does not imply differentiability. So I write that down as I hear you guys going, yeah. Okay, so they say that here, differentiability implies continuity. However, continuity does not imply differentiability. And that is something to make sure that you know. That just because it's continuous doesn't mean it's differentiable. Okay. And one last little thought here on this one, intermediate value theorem for derivatives. Okay, so go back to before we were doing in the intermediate value theorem was to prove that if a function is continuous, that given 2 points, we can identify another point between them. So an intermediate value theorem for derivatives, not every function can be a derivative. If a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. So back to when we were doing limits. You did a limit to prove that something was continuous. Now with derivatives, it's the same idea. If you have an interval, like this one says from a to b, now I can go, oh, I have an interval from 1 to 2 that is differentiable on every point between 1 and 2. That means the derivative will take everything beyond 1 and f prime at 2. Every point between the two it will take on those values. Anyways, so I can show that if this was a negative slope and this was a positive slope, that somewhere between the two, there was a slope of 0. Okay, so intermediate value theorem, show that the function is not the derivative of any function on the interval -1 to 1. Remember, differentiability implies continuity. Keep that one in mind. So if I do, so the function is not the derivative of any function. So really this is an f prime. So if I do the limit as x approaches 0 from the left of f prime of x, then that's going to be this one here, and I'm going to get 0. And then I go limit as x approaches 0 from the right of f prime, I'm going to get 1. So since the left limit, the limit as x approaches 0 from the left, does not equal the limit as x approaches 0 from the right, therefore, f prime of x is not differentiable on the interval of -1 to 1. Okay, which will also implies f of x is not, okay, actually f prime is not, I can actually go, is not continuous, sorry about that, continuous, I'm going to forget something here, which implies f of x, remember this is f prime of x is not differentiable. Sorry, I had them two mixed up. Is not differentiable on the interval of -1 to 1. It could, now we don't know what's wrong. It could be a jump. It can be a corner. It could, there's a lot of different things. We just know that f prime is not continuous on that interval. Therefore, so it's not continuous, which implies that it's not differentiable. That f of x, what it came from, is not a differentiable function. This one you don't get asked to work on a lot. It's just an idea to make sure you know. When we get to the next one, we'll get to integrals. That's when they get more involved in those. Okay, so this one was a much longer one than the first part of the video, but we'll live and learn. All right, good luck on that.